Hi, everyone. My name is Fabio Tosti, and I'm really very glad to be here today giving this keynote presentation for the 45th International Conference on Telecommunications and Signal Processing. Let me kick off immediately my presentation and share my slides with yourselves. As I said, my name is Fabio Tosti, and I am a professor of civil engineering and the deputy director of the Farrington Center for Non-Destructive Testing and Remote Sensing at the University of West London. The main focus of today's keynote speech is going to be around the ground-penetrating radar and satellite remote sensing methods for railway infrastructure monitoring. The layout of the keynote is the following. I will provide a brief introduction of the Farrington Center for Non-Destructive Testing and Remote Sensing, and also background and technologies that are related to the area of the transport infrastructure monitoring, which will be the main focus of today's keynote speech, as well as also the data processing and signal processing aspects related to it. Again, a bit of information background about railway structures and construction materials to understand the logic of the research behind this keynote. And then we are going to discuss about the ground penetrating radar technologies in terms of briefing about methods and mostly research application, and the multi-temporal interferometric synthetic Aperture radar techniques, again in terms of methods and applications. Finally, main conclusions, challenges, and future areas of development will be discussed. So a bit of background in terms of the Farrington Center for Non-Destructive Testing and Remote Sensing. Here you see the structure of the center. The center is led by Professor Amir Alani and myself as the deputy head of the center, and it can rely on a variety of expertise from the engineering side, including civil engineering and electrical and electronic engineering background and expertise, as well as to the computer science side of the research, data management, expertise in artificial intelligence, machine learning, and also maths and stats expertise. The center can rely on associate members as well as a good cohort of research fellows and PhD students. The technology and expertise that we are using at the Farrington Center are various. As you can see here, there is a comprehensive list of technology that we are using, including ground penetrating radar systems from low frequencies to high frequency within the GPR frequency range, 3D laser scanner technology, and also we have expertise in InSAR satellite remote sensing, data processing and interpretation. We have equipment such as vector network analyzer systems, airborne interferometric radar systems, deflection-based methods, and also infrared thermal imaging. So as you can see, there is quite a various range of techniques and also technologies that are ranking basically our center within as one of the most equipped in the UK and Europe. So what is the background in terms of transport infrastructure monitoring, and what is the situation in this particular area? Generally speaking, traditionally, the area could rely on a standalone concept of using this type of technology. However, over the last few years, the research trends as well as the industrial application are evolving much more towards an integrated use of these types of technology. And that will be discussed in our keynote. Requirements. Well, nowadays, the civil engineering sector is in high demand of continuous, significant, and reliable information. And the current scenario is that high standards of data quality can be nowadays produced, as well as very accurate data. And this happens with either remote sensing and non-destructive testing technologies. However, we have to register that limitations are in place, and still they could represent a kind of bottleneck for the development of these technologies. And what I'm referring to is high costs and challenges for implementation at the network level. Remote sensing techniques are yet not fully recognized within the scientific and professional community for inclusion in what we name in the transport infrastructure area as infrastructure management systems. And also, data fusion algorithms are now in a stage that we can say that they are under development. So the trend, as I mentioned earlier, is that using integrated data collection and interpretation methods is seen to be as the future of this area. And obviously, this is where research also it is going to be focusing. When it comes to the non-destructive testing methods, specifically ground-based non-destructive testing methods, we have to register use of conventional testing methods. Examples are given in the slides, such as force and flat check tests. And these are usually very costly. They are invasive at different levels. And also the significance of data collected is relatively low because they provide information at the time and spatial sampling point. On the other hand, non-destructive testing methods, good examples are given in these slides in terms of GPR, ground penetrating radar laser scanner, and ground-based synthetic aperture radar. They are relatively low cost and they are non-invasive, and significance of the data is high, especially with the latest development in data processing and interpretation methods. On the other hand, the other major area that I'm going to discuss today in this keynote are the satellite remote sensing techniques. And one of the most popular is the persistent scattered interferometry, what is known as the PSI technique. And these rely basically on use of multi-temporal interferometric techniques. Again, these techniques contextualized within the area of transport infrastructure monitoring. You can see from the table how much of the sector they can cover, and practically this versatility is actually making these techniques very much popular, especially for the last decade. Now, going through a bit more the railway sector, it is important to give a bit of background on what is the significance of the research that is going to be discussed. Well, for your knowledge, two types of railway construction exist, and these are labeled as ballasted, so use of ballast materials that it's quite common in our nowadays everyday life, and ballastless railway tracks, which represents a lower amount in terms of the available railway infrastructure assets. So in fact, we can say that nearly 95% of railway structures are labeled as ballasted railways. So that is the relevance of this particular material where we are going to focus today. And then what are the benefits of providing services using ballasted tracks? Well, rail can allow for a more controlled guidance of the wheels. Sleepers, they are in controls of the rail's alignment, and also use of structural layers, foundation structural layers that we name in this sector as ballast and sub-ballast layers. They provide a proper bearing capacity and also water drainage capability. In the bottom part of the slide, you can see a typical cross-section structures of a railway ballasted structure, so that you can see that we are basically referring to a multi-layer structure with a superstructure, which is what we can see every day for these types of infrastructure. In terms of the material, the focus is much important because we need to understand how this material can deteriorate and provides decays in order for us to be able to give proper intervention and having a sort of early stage warning system for us to action maintenance intervention. So generally speaking, railway ballast is made of coarse crushed rock materials with a particular or selected particle size distribution, which is fit for the purpose of the application. From the table, it can be seen that there can be used several different materials of a variety of gradation. So overall, ballast materials allows for good elasticity properties, low construction costs, especially if compared to ballasted tracks, and also a relatively ease of construction and maintenance. On the other hand, and this is where the problems comes, and this is where research is focusing in order to provide a good interpretation of the decay process, ballast on the medium-longer term can cause loss of alignment for the railway tracks. It has tendency to degrade quite fast. It is subject to decay effects such as the so-called pumping, and also it requires frequent maintenance activities. How does the deterioration of coarse ballast materials work? Well, there is something that in the subject area we call fouling, which is a process of ballast contamination. Usually fouling is materials with a size lower than 12 millimeters, and sources are different. It could be related to fragmentation of aggregates of ballast or to upward migration of fine material from the foundation layer. It could be caused by surface infiltration of weather particles or cold droplets, and also by the so-called decay effects of the sleepers. So technically, again, what is named as the sleepers wearing. So there is a variety of factors and sources that they can cause a contamination of ballast, and they can create the so-named fouling. Effect. Well, why is fouling so important, and why it deserves so much attention within the area of railway infrastructure? The provision of fouling generally affects the strength of the infrastructure. It limits the infrastructure resilience, and also it can inhibit drainage capacity and contribute to decrease material durability. Durability, as you might be aware, is a very important factor that now civil and environmental engineering practices are really looking at. So broadly, we can say that formation of fouling, so contamination of the railway structure, can definitely be linked to issues in terms of safety and the proper operation of this type of infrastructure aspect. What is done in terms of understanding the occurrence and provide accordingly counteractions? Inspection and monitoring activities are frequently provided by asset owners and stakeholders in charge for the maintenance of the infrastructure. There exist some established methods relying on visual inspection, which is still one of the most popular practice for the monitoring of these infrastructures. Sampling and analysis of the grain size distribution, direct analysis of the grain size distribution are also popular, and also monitoring of the track geometry, for example, using laser-based profilometers can be done. And if there is any misalignment, this can be indirectly related to issues and structural problems of railways. So as well as these established methods, nowadays, for the last few decades in terms of the GPR, but more recently for the satellite remote sensing technology, there exist other methods that are labeled as emerging methods. GPR, on top of these slides, it can provide detailed substructure detection with a kind of medium-high survey productivity, and also it can contribute to contain or limit somehow the service disruptions. Still, the infrastructure has to be used when GPR investigation are in place. However, as you can see from the slide in here, because these radars can be attached to the railway convoy, the interruptions to the service is really limited, and inspections can go at a good speed in around 100 kilometers per hour. Parallel to this, more recently, satellite remote sensing has emerged as a new area of science for transport infrastructure monitoring. With special reference to railways, what we can say definitely is that use of this technology can provide an early stage detection of critical sections in terms of the surface displacement that can be identified, and also a very high survey productivity and no service disruptions, because there is no need using satellite data processing and interpretations to close or disrupt any service at any given time. Very more recently, the use of these technologies is being applied in combination, and in fact, research is now directing towards an integrated use of these two particular techniques with very high productivity in terms of data collection and provision for the development of new multi-sensor and multi-resolution data integration programs for infrastructure monitoring. So far, that is a background of the sector, what is happening, and what are the new research trends and directions. So it is now time to get more into the research findings and the way it is going to be done. We will start from the GPR perspective to analyze the progress of research, recent progress of research, and then we will move towards the satellite remote sensing. A brief introduction of the ground penetrating radar technology. This is run as a non-destructive testing techniques using radio frequency electromagnetic energy for the assessment of subsurface or man-made construction, with the main plus of not affecting their original structure. So it's purely non-destructive. In terms of the working principles, on the left part of the slide, you can see a typical conceptual scheme of a GPR working process. So a transmitter antenna can send the signal on the subsurface, and whenever there is an interface, so an electromagnetic interface, the signal is reflected and captured by a receiver antenna, so that the signal then can propagate afterwards deeper and detect any other dielectric contrast anomaly that can be it is in the range of detection for the GPR. The output is a typical signal with amplitudes against time, and peaks are usually utilized to identify the geometric features and substructure of the detected medium. GPR is a technique that allows a variety of information to be processed from the A scan, which is what we have just seen as the elementary output of a scan, up to a number of B scans put all together aside that can generate the so-called radargram. Radargram at the center of these slides, it's a typical output of GPR. However, GPR outputs can be also analyzed in a 3D environment with collection of multiple B scans, and this can be further elaborated, for example, creating another bidimensional output now towards a different plane, which is named as the C-scan. C-scan is actually providing information in terms of the subsurface feature on a planar view concerning the area detected. GPR has been widely used in many disciplines, and this is one of the reasons of its popularity. The first use of GPR has been done in the military sectors as a mines detection tool, and then it has moved towards other areas, popular areas such as archaeology, geology, structural monitoring, and also utilities detection, bridges and tunnels, and to remain within the transport infrastructure sector, roads, railways, and airfields. So a wide variety of sectors covered, which makes these non-destructive testing methods perhaps the most popular within the range of NDTs available nowadays. For the research part and discussion of results, the way has been organized in these talks, we will go through scales and domains of research. So we are going to discuss outputs and research findings and new direction outcomes in terms of laboratory research, use of numerical algorithms such as the finite difference time domain and the random sequential absorption approach. And also we will see how GPR can be deployed and applied for experimental tests at the test site scale that can provide us with more insights on this type of technology. The first research that I would like to discuss today in this keynote is an experimental research done at the laboratory facility of Roma Tre University in Italy. There were multiple targets in this type of research, such as railway track structural component assessment. So the effect on the GPR signal of several factors were analyzed. One was these aspects, and then the other two were how the antenna properties can provide and can affect the GPR signals in terms of their frequency and dipole orientation, and also the effect of the ballast contamination on the GPR signal. And we have just mentioned the relevance of understanding level of ballast contaminations for railway infrastructure monitoring. The GPR systems that were used in this particular research were both air coupled with two different central frequencies of investigation, 1 gigahertz and 2 gigahertz, and ground coupled GPR systems as well with 600 megahertz and 1.6 gigahertz central frequency of investigation. As you can see from the slide, this is actually a collage of experimental setups. A formwork, flexible formwork where the aggregate size could be seen, where it was used in order to replicate typical ballast aggregate arrangement and several different levels of contaminations, from no contamination, which is 0, up to highly fouled conditions, which is condition number 3, were recreated using fines material, typically clay in that case. And also other reality-like arrangement have been created in the same experimental setup. For example, in here, concrete sleepers were manufactured and deployed in the middle of this formwork to recreate real-life condition, and several different radar have been used in a variety, as I mentioned, of frequency and dipole orientations to understand better and the response, the electromagnetic response of the material. In terms of the railway track structural components, so how sleepers and rails can affect the signal, you can see in here 2 different radargrams, 1 gigahertz and 2 gigahertz with sleepers. So the first row is the signal collected with sleepers, and the bottom radargrams are without sleepers. You can see that there is a difference in the signal output, and the interference given by the sleepers in cyan in these radargrams, it's evident in terms of the response that can be get from the signal, as the response when sleepers are present is actually hidden in the radargram. Again, the antenna in here has been moved from left to right in the towing direction, and signal has been collected in terms of its amplitude and analyzed for interpretation purposes. The way the antenna have been deployed in order to be able to collect data have been 2 longitudinal orientation. So the horn antenna has been deployed with a longitudinal orientation of their dipoles, and also in the orthogonal direction in order to recreate a transverse orientation of the dipoles. This is how the antennas actually could be seen in a real-life application of railway monitoring. In terms of the output, you can see 3 different signals in here collected with the 1 gigahertz antenna at different angles of dipole orientation, 0, 45 degrees, and 90 degrees. We can clearly see within the time window of reflections related to the ballast material that the 0 degrees antenna dipole orientation has high effects from the sleepers, as in here, whereas the 45 degrees dipole orientation had limited effects from sleepers and rails, which is a good result in terms of which dipoles orientation could be used possibly in order to get real-life detection of materials. The 90 degree, so the bottom one, has high effects from rails, which practically says that it is not recommended for real-life applications and for the high interferences of the rail. And also, one of the aspects that was analyzed in this research was the ballast contamination effects on the signal collected. This bar chart shows the trend of the dielectric permittivity for different types of frequency of investigation, from 600 to gigahertz, to 600 megahertz to gigahertz. And the way it was analyzed, the permittivity was mapped against different fouling conditions. So the green one is no fouling, up to the red one, which is high fouling level. The general trend, as you could clearly see, is that the higher is the fouling, the higher is the value of the dielectric permittivity, regardless of the signal collected, apart from one trend which was not coherent with rest collected for the 1 gigahertz antenna. And also another major factor that was observed was that when no fouling, so the green one, is analyzed, as opposed to the highest condition of fouling, the level of attenuation rate of the signal is much lower where no fouling is present, whereas the attenuation rate is much higher for highly contaminated conditions. So attenuation rate of the signal increases with fouling, which is another important indication that we can get. The second domain that it is worthy of discussion in this keynote is the numerical research developed using several different techniques and approach, such as the finite difference time domain and the random sequential absorption techniques. The logic of the research is summarized in the next few slides, these slides and the next few slides. So the first step is to define an investigation domain. Again, the lab formwork has been used in this case in order to identify a domain which could be comparable to the domain of ballast in real life tracklets. Second step was using information that we could get from the transparent, basically, formwork perspex walls. We have been able to estimate the particle gradings and to come out with an output in terms of the grain size curve and its typical distribution, aggregates distribution properties. The third step was to define a simulation domain and compaction condition using the random sequential absorption process. Specifically, step one was in terms of aggregates positioning. So aggregates have been positioned in the formwork within the numerical models, and step two of this third stage of the approach was constraining aggregates contact conditions in order to recreate real life light conditions. The final step within stage number 3 was to calibrate the aggregates compaction. Obviously, the aim was to provide a model which was the closest possible to real life condition, and that particular step allowed to recreate compaction conditions for the aggregates within the flow. The fourth and next major stage of this numerical research approach was use of simulation of the ballast electromagnetic response through a finite difference time domain technique. So finite difference time domain technique relies on the use of Maxwell's equations and the Yee's cell approach. The final output from this approach was to obviously recreate a time domain simulated signal that could provide us information about the goodness of the numerical model created with the RSA approach. So the output from the random sequential absorption approach at different level of contamination. So you see clean ballast, 10 centimeters, layers of filing, 20 centimeters filing layer and 30 centimeters filing layer represented the highest possible contaminated scenario, were provided to the electromagnetic model used for the finite difference time domain approach techniques, and signals were created. So simulated signal have been created, and simulated signal in these four scenarios are those with solid marker, and these were compared to the measured signal collected in the lab using the same type of GPR system. As you can see, the comparison shows a good agreement between the simulated program and the actual experimental signal collected in the lab, and that allows us to say that use of numerical modeling can provide accurate prediction of the ballast conditions, and also there is good prospects for incorporation of this numerical approach into early warning railway infrastructure monitoring systems. The next stage of experimental research for the ground penetrating radar technologies, it considered test site inspection carried out at Roma Termini railway station in Rome, Italy. The goal of this particular research was to assess the effect of the GPR signal for antennas properties in terms of, again, frequency and dipole orientation, and also the ballast physical properties, and the aspects that in here were analyzed were the aggregate fragmentation and contamination and the moisture. GPR systems used for this particular research were air-coupled systems with 1 gig and 2 gigahertz central frequencies of investigation. The map in here indicates the area of the major railway station in Italy where tests were carried out. The experimental program was quite comprehensive. In fact, as you can see, 10 different configurations of ballast contamination and also type of ballast were recreated. And also, in terms of the methodology, areas of inspections were obviously made equivalent in terms of dimension. This is the sectors that were analyzed, including presence of sleepers, and also in terms of the depth of the investigation. So actually, homogeneous conditions for analysis of materials have been recreated. Some photographic materials to show the stages of the condition preparation, so those 10 scenarios preparation. Ballast was put within the sleepers in order to provide those domains, equivalent domains for those 10 conditions analyzed, and also the ballast was polluted, was contaminated at different levels. Another physical property that was analyzed in terms of its effects on the GPR signal was water content. Several different water contents were recreated. The environmental moisture condition was 5%. So that was considered within the context of the data interpretation. And also water was added artificially in order to recreate highly percentage of moisture in around 20%. And evaporation of water allowed to recreate a third scenario, and it was measured that around 12% of water content could be associated to this particular scenario. In terms of the GPR antennas, 2 gigahertz and 1 gigahertz antennas were used, and also 3 different dipoles orientation have been analyzed, similar to what it was mentioned earlier in the lab environment. 0 degrees, 45 degrees, and 90 degrees of antenna orientation have been analyzed. Here, a summary of main results. You can see 3 columns where 0-degree orientation, 45-degree orientation, and 90-degree orientation have been used. And as the outputs of the analysis, the spectrum, the frequency spectrum of the signals that were compared each to one another. In terms of the major output for the new ballast, which is the solid line within the spectrum, semi-crushed, dashed line, and fully crushed are the dotted lines in these spectra. The cyan1, the cyan colored spectrums are related to the 1 gigahertz frequency spectrum. These spectra have been collected and have been labeled as those with the highest variation, either in terms of their amplitude and their spectral shape against the fragmentation rate. In fact, you can see that the shape of the spectra is quite different according to this particular factor. Another major outputs that were achieved with the 2 gigahertz antenna were in terms of the frequency spectra variation, and reference is to the shift of the frequency spectrum peaks in terms of against the fragmentation rate. So the highest is the fragmentation rate, then the more shift is observed for the frequency spectra. And also another major point which was observed was in terms of the frequency spectra collection for the new ballast. They show that most of the energy concentration is at lower energy, so in the lower part of the frequency band. So again, are the results that are useful in order to be considered for data interpretation in real life scenario. In terms of the analysis and results for the fouling, so the contamination against the moisture content, here again a plot that shows the different fouling level, low, medium, and high, against the level of humidity. The level of humidity in these 3 graphs, it increases from top to the bottom. Generally speaking, effect of contamination, so effect of contaminations can be seen from left to right. It is much more evident for high moisture content. In fact, the plot of the surface reflection amplitude for these scenarios is relatively flat for low level of humidity, while it becomes quite apparent, quite evident that there is something when the humidity is very high. Also, in terms of the effect of humidity on the signal, from top to bottom, increase of water content is much more evident when it comes to highly fouled ballast. In fact, you can see that in this window in here, highly fouled condition, it is very clear that as soon as the humidity increases, then the signal in terms of surface reflection amplitude does if ballast is highly fouled, highly contaminated. And also surface reflection amplitude is quasi-horizontal for these conditions, so the fouling level equal to 0 and low water content, whereas at the opposite, it is maximum when fouling is higher and humidity level is higher as well. So the general conclusion for this type of analysis is that fouling contamination in trackpads is more. And as a confirmation of what we just said, are these outputs from same signal, but in here analyzed in terms of their short-term Fourier transport, STFT. can clearly notice that the opposite condition, so no contamination and low humidity, is very much different in terms of the highly contaminated and highest humidity in terms of their response. So again, another confirmation that wet conditions can support interpretation of fouling, and this could be a good finding for real life inspection as well. Now, we have covered the GPR area. It is now time to move to the second major technology covered in this keynote talk, which is the satellite remote sensing sector, more specifically the multi-temporal interferometric synthetic aperture radar technique. A bit of background, satellite remote sensing, it was mentioned earlier, but the coverage for these techniques is very high, very large areas can be covered. System operation is independent from weather conditions, so in fact, signal can penetrate through clouds and rain, although there are components that needs to be accounted when the phase is processed and the outputs are analyzed. Accurate measurements of the distance between target and the radar by means of the interferometry. And also, one of the major pluses is that these type of techniques can provide very dense data sets that can be updated with the very, very high temporal frequencies. And they lend themselves for integrations with other systems and methods, as mentioned. For example, GPR is really a new trend line of research in the infrastructure health monitoring sector. In terms of the technique, the remote sensing, it uses satellite to detect displacements at the ground level. These satellites, they are equipped with radar sensors, and they are working at in a range of height from 500 to 1,000 kilometers from the Earth's surface. And also the sensor mounted in these satellites, they can work at different bands, depending on the resolutions that we would like to analyze our data. And the bands are displayed in here. In general, the motion of the satellite is utilized in order to for the system to work as a large virtual antenna that has capability to collect very high resolution images, and the potential is clearly understandable. An example of how how displacements related to infrastructures can be collected. A satellite can orbit at the time t0, and after a certain time of acquisition on the same orbit, and collect data in terms of differences, if there is any difference of the displacement, with a variety of revisiting time. It could be 35, 24, or 12 days. This is the frequency that data are collected. The detection works on the principle of difference of phases of the signal that allows to, within a framework of a multi-temporal observation, they allow to detect displacement over time in terms of their displacement rate. So this technology allows to detect the velocity whereby soil or structure can displace over time. In general, three major stages. Statistically stable scatterer points or scatterers are detected by analysis of these images collected at different stages in time. And second step is analysis of image range variation, again, to understand if there is any gap in terms of the phase that can be linked with the displacement of the structure. And then maps such as the displacement velocity maps can be generated that are fundamental tools for analysis of structural movements or displacement. To provide a measure of the potential of this technique, a real-life application is discussed in here in terms of a case study developed in south of Italy with the support of Ferrovie del Gargano. And the goal was to provide a structural health monitoring of a ballasted railway network. In that case, two different data sets have been used, C-band data from the Sentinel-1 mission and Cosmos SkyMed datasets have been used, covering a period of nearly 2 years, from 2016, early 2016 to January 2018. In combination with this technology, GPR radars have been used, and here an account of integration between these two techniques is also given. The GPR systems were mounting 1 GHz, 1.5 GHz, and 2 GHz antennas in an air-coupled configuration. The distance that was covered was around 12 kilometers, and with a type of railway service which is currently operational and good trackbed condition. The PS InSAR interferometry allowed to provide network level analysis. And as you can see, these green points, they are all scatterers that have been used in our analysis. And the blue dots in here are mileage points. Thresholds are set in terms of displacements in order to identify potentially critical sections. And generally speaking, regarding the investigated section, two critical sections were identified with significant displacement velocity using the InSAR analysis. So the InSAR analysis were covering the network level analysis, whereas more detailed analysis on spot could be done using GPR system. And again, an example of what it has been done with the InSAR maps, a map of displacement over time, so over the time of investigation could be generated. And where critical sections have been identified, GPR investigation has been carried out. And in terms of the interpretation of these results, as you can see from these GPR radargrams, where interfaces between the substructural layers of the track beds have been identified, these white interface, which is the interface between the sub-ballast layer and the subgrade, at some section it gets interrupted. And this has been related by the presence of fines materials, typically clay, which is known to have a highly attenuation effect on the GPR signal. And this has happened exactly at the critical sections identified by the satellite investigation. Another aspect that could be assessed using the PS InSAR interferometry in combinations with, for example, GPR systems is the abutment area, so the interconnection area between normal track beds section and the bridge decks, basically railway bridge decks that are a part of railway infrastructure. So in that case, the area, the zoom is on areas of significant subsidence at these intersections between the rail and the abutment section of this railway bridge. And that was identified by using the InSAR analysis. Now, these analyses were cross-validated by GPR investigation. And as you can see, there is a nearly regular pattern with no missing information in terms of signal interface reflection. So that means that the interpretation was that no construction-related issues at the rail abutment section have been identified. And the diagnosis was that improper compaction of the ballasted layers could have caused these differential displacements that were detected using the PS InSAR interferometry at large scale. So generally speaking, the PS InSAR can provide lots of information about the movement of structures and with a research perspective, future research perspective, we can also say that data correlation analysis can definitely support the diagnostics of decay for critical sections in rail. So to conclude, a few points. Excellent progress have been achieved in terms of the high standards of quality of data and their accuracy with both ground penetrating radar and satellite remote sensing technologies. Research discussed has showed that quite good amount of key informations have emerged for practical use of air-coupled GPR systems for the assessment of the degradation and contamination processes related to ballast. Also, the dipole orientation and central frequencies of antennas, they have shown a different electromagnetic response for detecting structural configuration of railway tracks in terms of their interrelations with the sleepers and rails. And also, ballast contamination itself by fouling can affect the GPR signal based on the physical condition of the railway tracks in a variety of manner. And also the antenna characteristics in terms, again, of their frequency and dipoles orientation. It has been shown that moisture content of railway tracks could be a relevant factor to assess and identify critical sections hit by this fouling contamination. And more general, GPR can be defined as a very suitable technology for integrations with other highly productive technologies such as the interferometric synthetic aperture, InSAR methods and techniques. And for this particular one, it is more recent compared to GPR, but it represents most valid and reliable method for network level analysis of surface displacements to be integrated with more detailed analysis that can be done with other techniques. Main challenges that have emerged from the analysis and the talk. Ballast formation mechanisms are various. We have seen it at the beginning of the keynote. So that means that because of this level of complexity, dedicated models, for example, fine-tuned models, can be required for detecting different sources of ballast contamination. And also, permanent scattered approaches are various, but each of them has got some limitation that can limit applicability in transport infrastructure engineering. And another major point that can be connected to the concept of integrating data is related to gaps in quality and type of information from the available techniques. So gaps exist. However, if these gaps in terms of information are clearly identified and also the actual needs for transport infrastructure monitoring per sector are clarified, this could become a big potential in the area of transport infrastructure monitoring. However, it is still a big point of debate. And finally, in terms of the main challenge is satellite remote sensing has not yet gained full recognition within the scientific community, but certainly with progress in research, it can potentially become a fundamental tool for integration in infrastructure management system. Areas of development, I would say orienting research towards filling the gap due to standalone use of individual technologies and promoting their integration. For example, because of the provision of many datasets information very much frequently updated, use of advanced machine learning and deep neural networks algorithms can support this process, develop an all-purpose GPR data processing framework for datasets preparation, investigate into the development of new potential SAR analysis method that can be served by using innovative permanent scatter approaches, for example, use of nonlinear displacement models or integration between existing permanent scatter approaches such as the DSI and the SBAS, and also developing more advanced infrastructure management systems with capacity and resources to integrate GPR and other remote sensing technologies at the network level. So these are areas of development that I believe could be looked at in the near future. These are my contact, and if you wish to inquire more about the content of this keynote talk, please feel free to email me or contact me at your convenience. And also special acknowledgement to research collaborator of the Faridan Center for Non-Destructive Testing and Remote Sensing, Professor Andrea Benedetto, Dr. Luca Becchi Ciampoli, and Dr. Valerio Gagliardi for their support and valid collaboration from the Department of Engineering at Roma Tre University in Italy. Thank you very much for your attention. It's been a great pleasure, and I hope you have enjoyed this keynote presentation. Thank you very much.